Firyuza and Yanchilina. Today we've got a real detective story from general relativity. We're gonna talk about the second era in Schwarzschild's solution. I believe this era is the most significant one. Why? Because it's obvious and highly revealing for general relativity. Why do we focus so much on Schwarzschild's solution? Because it's the only solution within general relativity that can actually be tested experimentally. Einstein's main equations are written in tensor form for curved space-time with a locally pseudo-Euclidean metric. These equations have never been directly tested in experiments, and there are no plans to test them anytime soon. So the only experimentally tested equation in general relativity is Schwarzschild's solution. In that sense, it's the most important one. Our main character today is the time component of the metric tensor. Here's what it looks like. According to general relativity, this component determines the rate of time in a gravitational field created by a mass m. You're already familiar with this equation from the video about Schwarzschild's three eras, as well as the video on the first era. Now we'll move on to the second era. Let's take a closer look at the equation for the rate of time and square it so the square root doesn't get in the way. I deliberately placed a plus sign in front of the 1 to emphasize that it is positive. However, the correction term that arises due to the presence of the mass m is negative. Take a close look at this equation. Inside, there is a positive 1, and from this 1, a certain quantity is subtracted. This quantity is proportional to the mass, inversely proportional to the distance divided by the square of the speed of light and multiplied by 2. So the structure is very simple. There is a positive 1 and there is a subtractive contribution created by the mass m. Let's keep that in mind. Suppose m is the mass of the Earth and r is the Earth's radius. In this case, dt is the time interval measured far away from the Earth, and d tau is the time interval measured on the Earth's surface. So far, everything is straightforward. We live on the surface of the Earth. The rate of time here is determined by the Earth's gravity. According to general relativity, the closer you are to the surface, the slower time passes. The average distance from the Earth to the Sun is about 23,500 times greater than the Earth's radius, but the Sun's mass is about 333,000 times greater than the Earth's mass. Since the contribution is determined by the ratio of mass to distance, the Sun's contribution to the rate of time on the Earth's surface is about 14 times greater than that of the Earth itself. So despite the enormous distance, the Sun affects the flow of time on Earth more strongly than the Earth itself. Think about that. But the Sun is just one of billions of stars in our galaxy. How do all these stars affect the rate of our time? We can roughly estimate how many times the contribution of our galaxy exceeds that of the Earth. To do this, we divide the total mass of our galaxy by its approximate radius and then compare this ratio with the same ratio for the Earth. The total mass of all the stars in the Milky Way is about 100 billion solar masses. The average radius of the Milky Way is about 50,000 light years. If we carry out simple calculations, we find that the contribution of our galaxy to the rate of time on the Earth's surface is about 500 times greater than the contribution of the Earth. This means that the rate of time on Earth is determined not by the Earth, not by the Sun, but by the Milky Way galaxy. But that's not all. There are billions of galaxies in the universe. How do they affect the rate of time here on Earth? The Milky Way is part of the local group of galaxies, which also includes the giant spiral galaxy Andromeda, the Triangulum galaxy, and about 100 dwarf galaxies. This entire group lies at the very edge of the local supercluster of galaxies. At the center of this supercluster is a massive cluster of galaxies in the Virgo constellation, which contains about half of the total mass of the supercluster. At the very center of the Virgo cluster is the famous galaxy M87, which we've already discussed in 3 videos in connection with the so-called image of a black hole's shadow and the relativistic jet emitted from its core. The total mass of the local supercluster is on the order of 10 to 15 solar masses, with an average radius of about 55 million light-years. Let's estimate its contribution to the flow of time on Earth. It turns out to be about 4,000 times greater than the contribution of the Earth. The local supercluster, in turn, is part of an even larger structure, the Laniakea supercluster, with a mass of about 10 to 17 solar masses and an average radius of roughly 250 million light-years. Its contribution to the rate of time on Earth is nearly 100,000 times greater than that of the Earth. Do you see the pattern? The farthest stellar system is from us, the greater its contribution to the rate of time on Earth. Why? The answer is simple. On average, mass increases in proportion to the cube of size, while the contribution to the rate of time is proportional to mass and inversely proportional to distance. That's why, as we move to larger and larger scales, the total contribution of distant structures to the rate of time near the Earth keeps increasing. As you've probably already guessed, the greatest contribution to the rate of time on Earth comes from the most distant galaxies. I've already discussed this in 2 videos about the gravitational potential of the universe. Let me remind you that the contribution of all galaxies to the time scale on Earth is approximately equal to 1. This is a well-established astronomical fact noted by many researchers, including Feynman. We discussed this in the video about Schwarzschild's first era. Now let's take another careful look at the equation for the rate of time. In this equation, the 1 has a positive sign, while the small correction to it has a negative sign. The small correction is the contribution of the Earth's mass, m, to the time scale near the Earth, and the 1 represents the contribution to that same time scale from all the stars and galaxies filling the universe. It is obvious that both contributions should have the same sign, since the gravitational nature of all masses is the same. But in this equation, that is not the case. The signs of these terms are different. This looks very strange, and the more you think about it, the stranger it becomes. Indeed, every mass is a source of a gravitational field. Every cosmic mass contributes to the change in the rate of time near the Earth and, in particular, affects the rate of atomic clocks. The Earth affects the rate of atomic clocks on Earth. The Sun affects the rate of atomic clocks on Earth. The galaxy affects the rate of atomic clocks on Earth. The massive galaxy cluster in the Virgo constellation affects the rate of atomic clocks on Earth. We expect all these influences to have the same sign. It would be strange if our star, the Sun, slowed down clocks on Earth while the galaxy made up of similar stars sped them up. So we assume that all stars and galaxies contribute with the same sign to the rate of time. But in the time equation, this is not the case. When we consider different cosmic objects, their contribution to the rate of time all have the same sign. But when we consider single mass within the time equation, its contribution carries a minus sign and opposed to the contribution of all other masses. In our case, the contribution of the small Earth is opposed to the contribution of the rest of the masses in the universe. But if we write the same time equation for the Sun, then the Sun's contribution will have a minus sign and will be opposed to all other cosmic masses. Why does this happen? Why do all masses in the universe act together, but when any one of them is inserted into the Schwarzschild solution, its effect on the rate of time acquires a minus sign and is set against the influence of all other masses? This is an obvious error. Why is no one paying attention to it? The only exception is Richard Feynman, who, after studying this issue, called it a catastrophe. He wrote about it in his lectures on gravitation, section 5.4. Mach's principle in quantum mechanics. Yes, this really is a sign catastrophe, and Feynman did not hesitate to call it that. Why did other scientists ignore the minus sign and simply overlook Feynman's lectures on gravitation? I think the reason is simple. For supporters of general relativity, the Schwarzschild solution is treated as the ultimate truth, beyond any doubt. For most physicists who are not deeply familiar with general relativity, the Schwarzschild solution is like a dark forest they never enter. That's why in my video, Schwarzschild's 3 errors, I try to explain in a simple and clear way that the Schwarzschild solution is not a dark forest, because the entire essence of this solution lies in a simple factor. This factor contains the entire meaning of the Schwarzschild solution. There is no other meaning in it, because if you remove this factor from the Schwarzschild solution, we end up with the classical equation for the square of the interval in spherical coordinates. Take a look at this factor. It's not difficult to understand the essence of this factor. And as we've just seen, that essence is an obvious contradiction. How did the minus sign end up in the Schwarzschild solution? Why can a solution that is clearly incorrect still produce accurate predictions? We'll answer these important questions in the next video. I'm Firyuza Yanchilina. Thanks for watching. Subscribe and leave a like. We're just getting started.